HXs, or sometimes just HX or HEX. Now, plate heat exchangers are very common. They are used extensively in building services and manufacturing. The reason they are popular is because they are very compact, they're very efficient, they're easy to service, they need very low maintenance as well. Their purpose is to transfer thermal energy from one fluid in one system to another without the two fluids mixing together. For example, in building services, you might want to transfer heat from a primary loop connected to a boiler over to a separate secondary loop, or maybe in a district heating network. Or in manufacturing, you may want to cool down some oil and use water to cool that down, but obviously you don't want to mix the oil and the water together. Now, if we pulled one of the heat exchangers apart, we're going to have a look at some of the main components here. So we've got the end plates here, or the front and back cover, and these are made from usually a mild steel, and they're very strong. They're there to hold everything together. Then we've got the nuts. These attach obviously and tighten up onto the tightening bolts. The tightening bolts, they fit in some grooves in there, and they'll run the entire length of the heat exchanger. And the bolts are tightened on these, and that will compress all the plates together and squeeze the gaskets against the plates to make the heat exchanger completely waterproof or leak proof. And then wedged in between there, we've got the plates where the heat transfer occurs, and we've also got the gaskets which sit in between the plates, and that's what gives it the seal. Larger heat exchangers will also have this supporting bar at the top and the bottom, and you can see here that the case and the plates, they just slide along there, and there's various ways that they can come off. Either they twist, these ones would be too big to twist off, but there's a section removed at the back where these will just drop out. But the smaller ones, these will just slide in and out. Now you can see a real plate, a heat exchanger plate there on the screen. Now these are typically made from steel or titanium, and you can see they've got this pattern grooved into them or stamped into them. These patterns are going to strengthen the plates. Obviously they're incredibly thin, and they're also going to increase the heat transfer surface area, as well as creating a very turbulent flow inside them. So it's not smooth. All the water has to rubble across these and come out very rough and turbulent. Now between the plates, we've got the gaskets here, just this rubber gasket, and that is attached to the face of the plate. And the purpose of the gasket is to ensure a tight fit and to prevent leaks. The gasket also allows or prevents the flow of fluid into the sheet. You can see here, so in this section here, we've got the rubber seal coming across and a double seal on this one, so that no fluid in this can leak out or flow in, as well as this side, whereas here there is no gasket there, so the fluid, if it entered here, it could flow down and come down and enter into this one here because there isn't anything there. Same as this one, the fluid can only come out of here and travel up and then into this section here, into that hole. Now you'll probably notice that the tightening bolts are, they extend far past the heat exchanger. That's for a few reasons. One is obviously to be able to fit all these plates and etc. on during the installation or during maintenance, but also this gives you the ability to extend the plate heat exchanger in future. So this one here is actually from a district heating network, and at the moment the building's only half complete and they're expecting to double the building size, so they've allowed extra bolt lengths to be added, and that means that the plates can be added and this heat exchanger can grow with the demand. Now there's a couple of ways that the plate heat exchanger can be piped up. This is the most common version, and the version that we're going to be looking at today. That is where the inlets and outlets are all on the front plate. So the fluids will enter, flow through their channels, and then make their way back to the front plate. The other version is where the fluids, one of the fluids enters through the front plate, and it passes through there and then makes its way, and it will then exit through the back plate, as well as one of the fluids will enter there as well. Now this version here, the first version, is the most common version, and that is because you don't need to alter the pipework if you need to extend the plate heat exchanger in the future, whereas with the second version here, all the pipework that's connected will have to be removed and remade to fit, depending on how far you extend your plate heat exchanger. So it's not really so practical. That is why this one is far more common. And you can just see in all these examples here, that is exactly what's happening. So the flow and return are happening on the front plate there. So how does it work? Well, we've already seen that if you remove some of the seal, then the fluid can flow through there. So if we stack a number of plates together, then you'll see it forms this channel, this pipe-like feature flowing through all the plates. And then we can add the front and back plates onto there, and we get these channels where the water or the fluid, whatever you've got, can then flow through certain plates, and it can't flow through other plates. And let's just see an example of how this would work practically. So if we open up the heat exchanger again, now you can see here that the gaskets is oriented differently on the alternating plates there for the heat exchange. So this one here, you can see a fluid in this pipe would not be allowed to pass through, or this one, and this one it would, so it just alternates vice versa all the way through. And so if we pass one fluid through there, you can see it entering through this top port, passing all the way through. It can't pass through this one, there's a seal there. You get to the next plate, oh, there's no seal there, so we can pass through there. Can't go into this hole, but it can go into this one because there is no seal. And so all these will pass through, collect up, and make its way back out. Now the same thing is going to be happening with the other fluid we're passing through. So you can see here we're passing a hot fluid through, and this one is entering through the bottom port, coming along. It's getting to the plates, and some of them it can pass through, so it will. Others it cannot leave that pipe, so it will not, and it will just pass through all the way until it creates that loop and exits. So if we mix these two fluids together, what's going to happen is the cold fluid is going to enter, pass through, and then on the other side of the plate is the hot fluid. So that is going to take some of that heat away, so the cold fluid will warm up, and that will leave as a much warmer fluid, and the hot fluid that comes in is going to cool down because it's going to give up some of its heat into the cold stream, and then that will leave as a much cooler fluid. So if we just look at a very basic example of how this is working, let's just say we've got a few plates here, and we've got a cold channel, hot channel, and another cold channel. Now if we let the hot fluid enter into the channel there, and as that happens, heat is then going to conduct through into the plates because they are touching, so that heat will then pass through and warm up this plate. And if we then pass the cold fluid into the cold channels, then some of the heat in those plates which have been heated up will start to cool down because some of that thermal energy is transferring over into the cold fluid. That's through conduction. And as that happens, the cold fluid begins to warm up, and obviously the hot fluid is going to start to cool down. So then the heat exchanger starts to equalize out, and that means that the cold fluid is going to exit warm, and the hot fluid is going to exit cool. And that temperature gradient is going to then vary through the heat exchanger, through the plates, and also through the fluids, which is conducting the heat. So when you combine all of this together, that is how you get the heat transfer occur in the plate heat exchanger. And you can also notice that these fluids are flowing in counterflow. Now that is the best configuration for the most effectiveness, because the log mean temperature difference, the LMTD, is at the greatest. We'll have a look at what that means in another video. This video is just for you to understand how it's working and why it works. I'll just give you a real world example of a heat exchanger here as well. So this is a German heat exchanger, as you can see written down here, but you can see this heat exchanger here can provide 1500 kilowatts of thermal energy, and has a transmission area of 29.3 meters squared with a flow rate of 43,000 liters per hour. It will also handle up to 100 bar on each side of the plate. So you can see these things are very powerful, and they're very efficient and very compact in how they work. Now, if you do have one of these in your buildings, please also remember to insulate this, as it's much more energy efficient, and keep the plastic sheets on the threads to protect them from damage. Otherwise you won't be able to get these nuts off very easily. Okay, that's it for this video. Thank you very much for watching. I hope you enjoyed it and it helped you. Please don't forget to like, subscribe and share, and if you have any comments, leave them in the comment section below. I'll try to get back to you as soon as possible. Once again, thank you very much for watching.
Exchanger. Now, heat exchangers have a lot of applications. You can see here this one's a car radiator. You're cooling down jacket water using air, and this prevents your engine from overheating. Another good example here is a home radiator, and you'll be using a liquid, usually water, to heat up air and keep your home warm. So these are both different types of heat exchanger. But in the industrial world, there's only two types of heat exchanger: a shell and tube type and a plate type. This is an image of a plate type heat exchanger, and we're going to go now and have a look at the model on the website and go through all the parts and explain some of the features. The design of the plate type heat exchanger is actually rather simple. The heat exchanger consists of a series of plates, and these plates are stacked one after the other. Between the plates you'll have warm and cold fluids, or at least warmer and cooler fluids. Now, because the plates are relatively thin and they have a large cross-sectional area, they have a very high heat transfer rate, and this heat will be transferred through the plates. So I've gone to the website and I've loaded the model, and what we're going to do now is talk through some of the main components. We zoom in here, we can see here this is an end plate. The end plate normally has 4 holes, 1, 2, 3, 4, and these will be inlet and discharge holes, and the 2 others will be for a cold fluid, an inlet and a discharge. If we go further here, we can see a clamping bar. On the top here we can see a guide bar. Further in we can see a black gasket. It's actually made of nitrile rubber. Behind it we have a corrugated metal plate, and this is where the plate type heat exchanger gets its name. Further back we have more plates, and here this is a plate stack, which is what it looks like when all the plates are pressed together. We'll have another end cover here which is removable, and as we can assemble all that, essentially everything will get pressed together. These clamping bars or screw threads will go into the holes here on the right hand side, and it will all be clamped together to a certain torque using a torque wrench. So now let's have a look at how exactly it works. Here we can see the appearance of a plate type heat exchanger when all the plates are separated out. Now, one of the most interesting aspects of the plate type heat exchanger is actually the nitrile rubber gaskets. That's these black gaskets here that run around the edges of the plate. And the reason why they're such a weird shape is because they're directing flow in different directions for each plate. As we can see here, the gaskets, they look similar, but each plate, one after the other, the gaskets will be rotated 180 degrees, and this rotation changes the way the fluid moves through the heat exchanger. Let's imagine for a moment that the plate has a fluid flowing through it, and this fluid is hot. So it would be coming through here, and it would enter the plate space. Now each of these plates are pushed up tight against each other, so the fluid will only ever be able to flow up to the boundaries of the gasket. And the boundaries we can see here. And then once it's occupied the whole space within the gasket area, it will exit through this hole here. So we have an inlet on the top for the hot fluid and a discharge on the bottom. Now let's imagine that we have a different flow coming in, and this time it's cold. Now the cold fluid is going to come in here, and the same thing is going to occur again. It's going to flow up to the edges of the gasket, it's going to occupy the whole area possible, and then when finished it's going to exit through this hole here. This will be the discharge for the cold fluid. Now you can notice that the fluids in the bottom here, the cold fluid comes in the bottom and flows out the top. On the other plate, the hot fluid comes in at the top and flows out of the bottom. This is known as contraflow or counterflow. It's the most efficient means of heat transfer, and that's why most heat exchangers will have counterflows or contraflows. It raises the efficiency of the heat exchanger. Now the gaskets that are forming the seal, these are not just ordinary gaskets. They're manufactured from nitrile rubber. They have a very good coefficient of elasticity. That means they can be heated up and cooled down without breaking. This is pretty useful if they're installed in the heat exchanger. They can also withstand temperatures up to 100 degrees, and this makes them suitable for a lot of industrial applications. You may have noticed that the plate isn't flat, it's actually corrugated. The reason for this is threefold. The first reason is that a corrugated plate gives it a larger contact surface area, and this contact surface area increases the heat transfer rate and makes the heat exchanger more efficient. The second reason is that a corrugated plate is actually stiffer than a flat plate, so you can manufacture a thinner plate, and this thinner plate has a higher heat transfer rate than a thicker plate. The third reason is that the corrugated plate creates turbulent flow. The turbulent flow prevents deposits forming on the plate, but it also has another function. It breaks down the boundary layer of liquids that may form on a surface. On the left-hand side you can see linear flow. Sometimes you'll get a boundary layer of liquid on the heat exchanger surface. This inhibits heat transfer and thus reduces the efficiency of the heat exchanger. On the right you can see we have a turbulent flow. This removes deposits from the heat exchanger surface and increases efficiency as no boundary layer can form on the heat exchanger surface. The plates themselves can be manufactured from a number of different materials, ranging from titanium to different sorts of alloy, as well as plastics. Titanium would be chosen whenever the environment is particularly corrosive. Titanium has excellent corrosion resistance characteristics, but unfortunately it's incredibly expensive. Another disadvantage when using titanium is that any metal connected to it will normally act as an anode. When two dissimilar metals are connected together, one will be an anode and one will be a cathode. The anode will slowly wear away due to galvanic action. Any metals connected to titanium plates will need to be protected, and this can be achieved by insulating the plate from the dissimilar metal or by installing a cathodic protection system. Other chemical processes may not be able to rely on metal alloys or titanium, and in these special instances the plate will be constructed of plastic or a polymer-based material. The advantages with plate type heat exchangers are that they are smaller and lighter than tube heat exchangers. They're also more efficient when compared to tube heat exchangers of the same size. They're easy to dismantle and clean, and they don't need excess space to dismantle. Tube type heat exchangers do need a considerable amount of space in order that you can clean them properly. This is mainly because you need to pull the tubes out. Plate type heat exchangers don't have this problem. In addition to that, the turbulent flow in the plate type heat exchanger helps keep the plates clean, and it also helps break down the boundary layer of fluids that build up on the plate surface. In addition to that, the plates are relatively easy to replace, and you can actually increase or decrease the heat transfer capacity of the unit by adding or removing plates. The downside to plate type heat exchangers is simply that they're expensive, or they can be if using materials such as titanium. Even the nitrile rubber gaskets themselves are quite expensive. It's difficult to find leaks because it's not possible to pressurize each plate individually. Normally, you'll need to use a non-destructive testing technique in order to find a leak. The nitrile rubber gaskets themselves are also quite difficult to replace. They're adhered to the plate and are quite difficult to remove. On land, you could send the plate away to a factory and they would use liquid nitrogen to freeze the plate and the gasket and then simply knock the gasket off. Unfortunately, if you're in the middle of a desert or on a ship in the Atlantic Ocean, this is not really a feasible option. The only feasible option is to carry spare plates and replace the plates in their entirety rather than trying to exchange the gasket. Another disadvantage is that if you over-tighten the clamping bolts when assembling, you'll actually crush the corrugated plates. This can seriously damage the plates and reduce the heat transfer rate. This reduction in heat transfer rate also causes a reduction in efficiency. A solution to this is to use a torque wrench when tightening the clamping bolts in order that you don't crush the plates.